When we have two or more equations, we call it a system. A system of equations is a set of two or more equations. A linear system consists of two linear equations. And when we talk about the solution of the system, it's the variables that make both equations true. So we know that a solution to an equation is what variable we plug in to make the equation true. Or sometimes when there's two variables, what ordered pair we plug in to make the equations true. So with a system, the ordered pair that is the solution is the ordered pair that makes both equations true. So we can algebraically check to see whether an ordered pair is a solution to a system by plugging in the ordered pair into the equations. So I'm going to check to see for this system, is 2, 2 a solution to the system? So I see that I get 6 minus 4, which equals 2. So that is true. And then if I plug in 2, 2 into the second equation, I get 2 plus 4, which is also 6. So 2, 2 is a solution to the system because when I plug in 2, 2 for x and y, it makes both equations true. And so I'm going to check to see if 0, negative 1 is a solution to this system. So I'm going to plug 0, negative 1 into both equations. I get 2 equals 2, so that's true. But if I plug 0, negative 1 into the second equation, it does not make the equation true. So 2, 2 is a solution, but 0, negative 1 is not a solution. And we can see to the right, I've graphed the two equations on Desmos. We can see that 2, 2 in a graph is the ordered pair that satisfies both equations, and on a graph, it's the point of intersection. So when we're looking for the solution to a system by graphing, we're looking for the point of intersection. So we can solve this system by graphing by finding the point of intersection. So if we're going to use our calculator, we need to remember that our equations always must be in y equals form. So I'm going to go to my calculator, and I know that if I put equations into my calculator in y equals, they always have to be in that form, y equals. So what I did was I took these two equations and I put them both into slope-intercept form, and I'm graphing them by hand. So I'm going to graph them by hand. So I'm going to plot 1/3 of my y-intercept, and I'm going to go up 2 and over 3. Graph that line. And then I'm going to graph negative x plus 3. And I'm going to graph that line. And I'm going to graph them on my calculator, but I see that the point of intersection of these two graphs looks like it's probably around 2, 1. So let's check, let's verify. So I went to my calculator and I put in 2/3 x minus 1/3 in y1, and then in y2, I went down to y2 and I put in negative x plus 3. And then I'm going to look in the standard window, so I'm going to press zoom 6, and I see that there is a point of intersection. And the best, most accurate way is to use what's called the second calc intersect feature, which is the second function on the trace button. So I'm going to press second trace for calculate, and I see on number 5 says intersect. So second calc intersect will allow me to find the intersection between two graphs on my calculator. So that's exactly what I want here. So I'm going to press number 5. And when it asks me at the bottom for what's the first curve you're finding the intersection of, and at the top, I'm on the blue graph, that is definitely the first one. So I'm going to press enter to say yes. And then when it asks me what is the second curve you want to find the intersection of, and I look up at the top and I see y2 equals negative x plus 3, that is definitely the second curve. So I'm going to press enter again. And when it asks me to guess, I'm going to press enter again. So I basically just press enter 3 times, and I see that the intersection is x equals 2, y equals 1. So one more time, let me show you one more time. We go second trace, which is second calculate, number 5 for intersect. When it asks me first curve, second curve, I just keep pressing enter. And when it asks me to guess, I press enter again, and it gives me the point of intersection. I can also find point of intersection sometimes using the table feature on my calculator, which is the second function on the graph button. Second graph says table. So I can always go to the table, and it gives me ordered pairs on the graph. So for y1, and then the third column is for y2. So I can see that when x equals 2, y equals 1 for both graphs. So that is definitely my point of intersection. Okay, so for this next one, we're going to put the next system in slope-intercept form. And for the first equation, I get y equals 3 over 2x minus 3. And then for the second equation, I put the second equation in slope-intercept form. And I see that I get y equals 3 over 2x minus 3. So in this case, I have y equals 3 over 2x, up 3 and over 2, minus 3. And if I were to graph the second equation, then I would be graphing exactly the same line. So in this case, we say that the lines are coinciding, which means they're the same line. And so we say that they intersect infinitely many times. And then the last example of graphing, we're going to put these two equations into slope-intercept form. So I get y equals 3 over 2x minus 3. And then I'm going to solve for y again. And I get y equals 3 over 2x minus 1. So notice these two lines are not the same line, but they do have the same slope. So I know that 3 over 2. So I know that lines that have the same slope are parallel. And so if the two lines are parallel, I know they will never intersect. So if the solution is on the graph at the point of intersection, and these lines are never going to intersect, then we say that there is no solution to this system. So we've looked at the three possibilities, and let's do a little application, and then we'll put it all together. Okay, so the diagram shows bird lengths and growth rates of two species of sharks. So we've got a Greenland shark that has a birth length of 37 centimeters, and grows, which means we're going to add grows at a rate of 0.75 centimeters per year. So there's the equation for the Greenland shark. And then we've also got a spiny dogfish that is born at 22 centimeters. So it starts at 22 centimeters when it's born, and it grows at a rate of 1.5 centimeters per year. So that's for the spiny dogfish. So we've got a system. So the first question is, at what age would a spiny dogfish and a Greenland shark be the same length? So we want to know at what x value would the y value be the same. So I need the point of intersection. So I'm going to go to my calculator, and I'm going to put in, I'll clear these two from last time. I'm going to put in 37 plus 0.75x. And then on y2, I'm going to put in 22 plus 1.5x. So I need to expand my window. So I know that x represents how old the fish is. So I'm going to go to window, and I'm going to change it to like 30 years. I don't think a fish would live more than 30 years. And I know that y represents the number of centimeters of the fish, or the length of the fish. So I'm thinking maybe 50 or 60 might work there. So I'm going to press graph, and I'm going to see that I don't see the point of intersection yet. So I still need to go up a little bit. So I'm going to go to window again, and I'm going to change my y max to like 75. And I'm going to see if now I can see where the point of intersection is. So I'm going to do second calc, number 5, press enter 3 times, and it gives me 20, 52. So that means that at 20 years, the age of 20 years, they will be the same length. They will be 52 centimeters. And then the last question is, if the growth rate